I'm going to talk about work done on water tanks in this series, and the part one is what is the idea behind solving these problems? So, work done is the amount of energy transferred to an object by a force acting under it with some displacement. So, if we're going in one direction, the work is going to be force times displacement. So, for an example, if we know that a person pushes on a box with a force of 150 newtons and they move the box 2.8 meters, then they will do 420 joules of work. So let's change the problem a bit. We're going to instead put a tank full of water and we're going to ask how much work is done to pump all that water out of the tank. And we know that the work done is the force times displacement. So let's kind of look at what this means. So we're trying to figure out how much work it takes to pump water out of the tank. So the displacement's going to be how far that water travels up to get out of the tank. So we can see that if we have water at the top of the tank, that water to come out the top is going to take not very much distance to travel to get out of it. But if we take water towards the bottom, it's going to be a lot more. So that displacement is going to be a lot bigger. So the displacement is going to change throughout the tank. Okay, so we want to use a formula. We want to use work as force times displacement, but our displacement is changing depending on where we are. So what do we do in this case? We are going to slice it up into tiny intervals. We're going to pretend that displacement is constant on each interval and use our formula. We will sum up all the work done on every little slice, and we will take the number of slices to infinity, and then we'll get the definite integral. All right, so let's slice it up. And we want to figure out this formula for displacement, so let's just take a test slice to kind of get an idea of what's happening. So this test slice starts from the bottom of the tank. It's 4 feet up from the bottom. And so it's going to take 6 feet to get out of the tank because the tank is 10 feet high. And let's pick another slice that's very close to the bottom of the tank. It's only 1.5 feet from the bottom. This one's going to take 8.5 feet to get out of the tank. And let's start with one at 8.25. So that would take 1.75 feet to get out of the tank. But we don't want to do that for infinitely many slices, so we're going to pick a random slice and just call that distance from the bottom to that slice x. And we see that the displacement's going to be 10 minus x because that's the pattern that we've seen. And because the tank is 10 feet high and x is the distance from the bottom. Okay, so we have our displacement. It's 10 minus x. So what is the force? So the force is just going to be the weight of the water. So we just need to find the density of a water slice times the volume of the water slice to find the force on that water slice. Because remember, we're just looking at one slice. So the density of the water is just, it doesn't matter if it's a slice or the whole tank, it's going to be the same thing. Now to look at the volume of one of these slices. So we have that the width is going to be the same as the tank at the bottom at 3, and same with the other side. And so the volume of that rectangular slab is just going to be length times width times height. And remember the height is dx because it's just that tiny little slice. And so the force is going to be the density times the volume. And the work done on one little tiny interval is going to be force times the displacement. And so we fill in the force. So we have the work on our tiny slices, and we're going to sum those up and take the number of slices to infinity, and we get the definite integral. So, so one last thing about where these bounds come from. They go from 0 to 10 because remember those integration bounds have to do with where we draw our slices, where we break up our interval. And that's going to be where the water is because the water is what we're pumping out of the tank. All right, thanks for watching, and I'll see you at the next video.